We come to our last speaker during the first session. It is Ghassan Fawaz, and he's a PhD candidate in the Department of Civil, Architectural and Environmental Engineering at the University of Texas at Austin, and he's working with Juan Mosiadelso, who is also a co-moderator of this session. Ghassan is also the current vice president of the EERI UT chapter, and his research interests include concrete behavior and the effects of earthquakes on reinforced concrete structures. And as I mentioned before, his presentation will be also on shape memory alloy bars, and his presentation is named Bond behavior of ribbed iron-based shape memory alloy bars embedded in concrete.
Thank you so much for the introduction. I'm Ghassan Fawaz, and today I will talk to you about bond behavior of ribbed iron-based shape memory alloy bars embedded in concrete. I want to acknowledge the contribution of my advisor, Juan Murcia-Delso, who is a professor at the University of Texas at Austin. So first, and this is a very nice parallel study with the previous presentation done by Professor Billa, who studied the bond behavior of shape memory alloys. And in this study, we are studying the bond behavior of iron-based shape memory alloy bars. So first, what are shape memory alloys and why are they good for structural engineering applications? Here I'm showing a nice plot for the different properties that shape memory alloy bars can give. So as we can see, the behavior of SMAs or shape memory alloys depend on stress, on strain, and on temperature. And if we are below a certain temperature, which is called the martensite temperature, the material exhibit what is called the shape memory effect. And essentially, after loading and unloading, we can recover the deformation by heating the material. If we are beyond another temperature, which is called the austenite temperature, the material exhibits the superelastic behavior. And this is again for nickel titanium-based shape memory alloys. But we are more concerned about the shape memory effect, which is more relevant to iron-based shape memory alloys. So basically, at ambient temperature, we pre-strain the material, and then upon heating, we can recover this strain. Of course, this will happen if the material is free to move, and if the material is restrained, for example, by clamping or by any bond with another bar or with another material like concrete, for example, then a pre-stressing stress is developed. And this is a motivation for pre-stressing applications using this material. What I'm showing here is a study by Shin and Andraus, and they used nickel titanium-based shape memory alloys in order to confine concrete using the shape memory alloy effect that I just mentioned. But the problem with this material is that it's very expensive, and it might not be practical for structural engineering applications if it's needed to be used at a larger scale. And recently, a new material was developed. It's iron-based. It's cheaper. It doesn't have the super elastic property as a nickel titanium-based, but it still have the shape memory effect. As we can see here, we have them in strips. We have them in ribbed bars, similar to conventional steel rebars. Here we have a study about strengthening a beam using those bars. What they did, they provided a shotcrete layer, and they embedded those bars, and they used the heating activation in order to induce a pre-stressing force in the beam, and that resulted in improving the cracking moment capacity and the performance of the beam. With that being said, this material is being used more and more, and different researchers are investigating it. And for that reason, it's important to understand the bond behavior of this material. And of course, as we all know, that bond has been extensively studied for conventional steel rebars, but still this material is a different material for different reasons. First of all, it has different mechanical properties, and also due to the activation temperature that we need to do in order to activate the shape memory effect, there might be a possible deterioration of the material while activating the bars. And this was already shown today by Professor Sharma, who presented the first presentation, and he showed us that even for conventional steel rebars, we can see that there is a bond reduction as the temperature increases. We have a bond reduction. As for shape memory alloys, Professor Billah just presented his study about nickel titanium based shape memory alloys, and we had his results. We just saw them. There's only one study about ribbed shape memory alloy bars, which will be used in this study, and those tests were done for near surface mounted application. So to this date, there is no study about the bond behavior of ribbed iron-based shape memory alloy bars, and this is what I will be presenting today. So the objective of this study is to study the performance of ribbed shape memory alloy bars for both splitting and pull-out types of failure, and then due to the possible effect of the activation temperature, we are investigating different temperature activations in order to see the influence of this temperature on the bond behavior and the bond strength. And finally, we will estimate the transfer lengths in prestressing concrete applications, because this material can be used for strengthening, can be used for concrete overlays, and then it's important for practical applications to get an idea about the transfer lengths for that material. So, okay, so this is material that we will use. This is a shape memory alloy bar, and I will just say shape memory alloy without saying iron-based, just to be more practical. And its the nominal diameter was 16 millimeter, which corresponds to number 5 bar. Here I'm computing the relative rib area for both the SMA bar and for the steel bar. And of course, we were doing the steel rebars for comparison purposes. Here I'm showing the stress strain plots for the SMA bars for 4% pre-strain and for 8% pre-strain. And here we are showing the strain recovered upon heat activation. We were able to get 1% strain recovery. Here you can see the yield strength of the material and the modulus of elasticity. This is very close to conventional steel, while the modulus of elasticity is smaller than conventional steel. This corresponds to around 24,000 KSI. So this is the material, and now these are the specimens. As I said, we are doing for both splitting and pull out. So we started with unconfined specimens and with confined specimens. Here, this is a rebar crossing the formwork. This is a steel tube or pipe that was used in order to debond the bar over the debonded length. This is a confined specimen. We just have the formwork, while for the confined specimen, the formwork was essentially a steel tube which stayed there. And the thickness of this steel tube was designed in order to ensure a pull-out failure. So the provided confinement was enough to ensure a pull-out failure. Here I'm showing the cross-section in both specimens for the confined and for the unconfined. We have the unbonded region and the bonded region. The bonded region was 5 dB. This is very commonly used when the local bond slip behavior is to be studied, because it gives a uniform bond stress distribution. And the unbonded region was done just to avoid the potential confinement from the bearing stresses during the test. So we will have a more objective results for the bonded region. The concrete compressive strength was 45 megapascal, which corresponds to around 6.5 KSI. So the different parameters investigated in this study, we did 9 series of pull-out specimens with SMA bars and steel bars, again, iron-based, of course. We had confined specimen, which supposedly we wanted them to fail by pull-out, and unconfined specimen, which we wanted them to fail by splitting. since the temperature effect is very important, we considered also the activation temperature effect. We considered no activation temperature effect at all to understand the fundamental of the bond properties of this bar. And then we considered different temperatures which were reported in the literature for this specific type of bars. And as I said, the bar is used typically by pre-straining first and then activating it using the temperature. So we consider two pre-strain level, 4% and 8%. And again, those values are reported for this specific material in the literature. So these are two figures from the test setup, and it's the activation process. So essentially what we did first, we pre-strained all the shape memory alloy bars. All of them was 4% and one series was 8%, just to see the influence, if there any, of the pre-strain on the bond behavior. After that, we heated the bar, and the heating was done using an electric current. Essentially, we used like 600 ampere power source. Here I'm showing thermocouple, K-type thermocouple from both sides, just to make sure that the temperature has already reached the required temperature or the target temperature for both ends. And you can see this is just an insulating tape in order not to influence the readings of the thermocouple, since we have electric current crossing the bar. And that's it. When we reach the target temperature, we turn the power supply off. For the setup, we are using like standard pull-out test. Here is a specimen, and here is a machine used, an MTS machine. As you can see, the bar is pulled out while it's bearing on a steel plate. This steel plate is connected to another bottom steel plate, which is gripped at the bottom part of the MTS room. And the connection between the top plate and the bottom plate, this one and this one, was achieved with 4 rods, which I'm showing here. So this is for your convenience. You can see the force, the bearing stresses, and the reaction forces from the rod. Of course, from equilibrium, we can compute the bond stress from the force that the machine has generated during the test, depending on the bar diameter and the bonded lengths. So before showing the results, I'm presenting here the mode of failure for both splitting failure and the pull-out failure. This was the splitting, cracked. It's very clear as we see. And when we open the specimen, it was already damaged. So you can see the splitting failure. And it's clear if you look here, the rib marks are still on the concrete. So there was no pull-out at all. It was pure splitting failure. And again, this is the debonded region, and this is the bonding region. For the pull-out failure, obviously, we needed to cut the specimen in order to see what happened inside. And clearly, you can see that the concrete between the ribs has been sheared off. Like you see, like here we have a smooth surface as compared to this surface, and we have concrete in between the ribs of the E-bar. So now I will show the bond slip versus bond stress for the different test series. And for your convenience, I'm presenting the bond stresses in both megapascal and KSI, and the slip in both millimeters and inches. First, I will show the comparison between the SMA bars with no heat activation versus conventional steel bars. This will be our benchmark, just to see how close or far the behavior is between the SMA bars and the conventional steel bars. And looking at both unconfined specimens and confined specimens, we can see a very similar behavior between both SMA bars and conventional steel bars. The only difference is the maximum bond strength or the peak bond strength, which was approximately around 20% lower for SMA bars. And if you remember, when I presented the relative rib area for SMA bars, it was smaller than the one for conventional steel bars, and this can be a reason. This can be a reason for this difference. But generally speaking, the behavior looks very similar: the ascending portion, the decaying, and the residual at the end. And for the unconfined, the specimen failed one of them for SMA bar, bars failed by splitting, and the other one failed by pull-out. But as you see, the maximum bond strength is very close. Apparently, this was the borderline between the splitting and the pull-out, and this observation has been already confirmed from other tests and other series that I'll present now. So after getting the general behavior of the SMA bars versus conventional steel bars, we need to investigate the influence of activation temperature, which we said it's very important for these types of bars. And what I'm showing here for no activation, for 160 degrees Celsius and for 300 degrees Celsius, this is for unconfined and this is for confined. Obviously, you can see major reductions in bond strength as you increase the temperature for unconfined specimens, while for confined specimens, there is not much reduction. For 160, it's almost similar to no activation. For 300, there's just maybe a 20% reduction, not more. Just to make it clearer for you, I'm summarizing the results in a table here. So SMA bars with unconfined, we have huge reduction in bond strength from 18.5 megapascal to 7.9 megapascal. While if you look at the confined cases, you will see a very minor influence of the heat activation as the bond just reduced from 22.5 to 20.3 megapascal. And these are the numbers in KSI, if you prefer the KSI unit. As I said before, we did one series with a different pre-strain just to see if there is any influence. And as you see here, there's not much of an influence. The 4% and the 8% are very close in terms of behavior, and this means that the behavior, they have very similar bond strengths. After comparing the shape memory alloy bars to the conventional steel bars, and after we found out that they are very similar, we decided to compare those bond behavior profiles to available models, and we chose two models: the commonly used FIB model 2010, which has both pull-out and splitting plots or models, and another more recently developed model by Murcia-Delso and Ching, which was developed specifically for pull-out failure. As we see for the unconfined case, the models are doing a very good job in predicting the maximum bond of SMA bars, and we are presenting here SMA bars with 160 degree Celsius heat activation, which will probably be used when those bars are used. And for the confined case, we see that SMA bars are giving higher bond strengths as compared to the models. Murcia-Delso and Ching model is giving closer result in terms of bond strengths, but in terms of the shape with the plateau of FIB, it's giving a better prediction. For the residual, we have very good predictions for both models. We're very close to the experimental results. So now, after understanding the bond behavior of SMA bars and the influence of activation temperature, we need to get an idea about the transfer lengths, because this will be a requirement when we are implementing those bars in practice. And in order to do that, I need to do just a quick review of the equilibrium here, that we have the mechanism of these bars. So first of all, when we activate those bars, a slip will be induced, and of course this slip will be resisted by bond stresses coming from between the interface between the bar and the concrete, and these will be required in order to develop the pre-stressing stress that we are assuming that the bar will achieve in order to use it for pre-stressing applications. So the slip will be maximum at the beginning of the transfer length. It will be 0 at the end of the transfer length, and the stress of the bar itself will be 0 here, and it will be the maximum or the target stress at this point. So from equilibrium, the force in the bar is equal to the force at the surfaces of the bond stresses of the bar. So we have the area of the bar multiplied by the target stress. This will be the force in the bar. And the bond stress integrated over the length, which is the transfer length in this case, will be the resisting forces. Accordingly, according to this equation, and according to a linear bond stress distribution, which was recommended by Murcia Delso and Fawaz 2019, this was an analytical model developed for conventional steel bars. It gave very good results when compared with experimental studies, and a linear bond stress distribution was found to be good in order to get very good predictions for bond strengths and development lengths. So we are using this assumption. With equilibrium and a linear bond stress distribution, we get a target stress equal to 4 tau average, the transfer length over the bar diameter. And as you see here, the linear distribution is going from, because it's linear and the end bond stress is 0, so we have 2 tau average, and this is tau average. And with the same model, it was recommended by Murcia Delso and Fawaz that the tau average is 0.27 tau max. Plugging the tau average in this equation, we get a transfer length equation, which is a function of the target stress, the bar diameter, and the maximum bond stress of these rebars. Here, by the way, I'm showing the bar stress distribution, and based on a linear bond stress distribution, we get a quadratic bar stress distribution. So now with this expression, the transfer length expression, we wanted to get an idea about the transfer lengths for the SMA bars, which were used for this study. And I'm using here a target recovery stress of 250 megapascal, which recommended by Michels et al. For this specific bar. We got a transfer length of 11 bar diameter for a 45 MPa concrete. This is, of course, for well-confined concrete. And of course, this is not a design value. This is an estimation, a minimum requirement in order, based on this specific bar, based on this specific material. If we want to expand later for design recommendations, like different bar diameters will be chosen, and also factors of safety have to be taken into consideration. So to wrap up, the bond slip behavior of ribbed SMA bars, iron-based, obviously, were similar to steel bars. The bond strength, however, was 20% lower. For the heat activation influence, we had major influence for unconfined specimens that reach 60% when the activation temperature is 300 C. While for confined specimens, we don't have that influence. They showed very similar behavior. And for that reason, the heat activation effect should be further investigated later. Also, research is needed to further characterize the bond performance for different bar sizes. Again, we use the 16 millimeter bar here. We need to check other bars, and for different concrete mixtures. Thank you so much for listening. I will be happy to answer your questions. This is my email, and this is the email of my advisor who was contributing to this study. Thank you so much.
Thank you, Ghassan, very much for your excellent presentation.